Hello to episode number 4 of the Device to Cloud series. In the previous episode, I've introduced a notion that I call service-assisted connectivity. Effectively, a device that's not able to defend itself gets help defending itself by never accepting inbound connections, but rather creating an outbound connection to a service that is actually powerful enough to go and take over the defense of the device. In this episode, we're going to go and expand on this and introduce the notion of intermediation. We're going to introduce a queue per device, and we're going to introduce also a feedback path, an ingress queue, which we can use to get feedback from commands and also to get telemetry from the device. Introducing this intermediation has a number of benefits, so I'm going to talk about the benefits for a moment until we get to the code. So first of all, what I'm doing is I'm separating out now the notion of an API on the front and a protocol head on the back, depending on how you want to take a look at it. The protocol head is the piece that talks to the device, and it speaks either a standard protocol, AMQP, MQTT, or whatever industry level protocols, device connectivity protocol you want, with the basic notion that the device always connects out. It connects into this device gateway, and the device gateway doesn't connect to the device, so the protocol needs to be suitable for that. So that's the basic protocol head. The API is how you project out the device access to that device to the outside world. HTTP is likely a good choice for that to make the device broadly accessible. So that cloud gateway is in the business of authenticating clients at the API side to make sure that that traffic is legitimate, that that traffic is actually suitable for the device, that the parameters are valid, etc., etc. It defends the device. If there's a true intrusion attempts, it will go and log them into an audit log. If it's alert worthy, it will go and alert an operator, etc. So it's going to do all the things that the device by itself, due to its capacity constraints, has a hard time doing. The queues in the middle are helping with that intermediation. So before I go into details of what the queues do, the first thing you get of that is the ability to go and independently scale the two parts, independently scale the API layer and the protocol head layer, because now you have this queuing mechanism in the middle, which means you can go and make n nodes, n servers that are dealing with the API front, and you can do n servers, likely more servers if you have thousands or tens of thousands of devices. And they are dealing with nothing more than terminating those connections that are coming in from the devices, dealing with higher density connections up the front. At the middle part, the way how the matchmaking happens is through these queues. In this model, and we're going to have variations of this, I'm going to talk through variations of this in some of the upcoming theory episodes in this hands-on series. Sometimes you have to do some theory in the upcoming episodes, so we're going to be that. Every device gets a queue. That's the simplest approach I'm going to start with. Every device gets its own assigned queue. So device number 1 has a queue, and I've created that in the Windows Azure portal. So in my namespace that sits in EU West, I have for that device now a queue, dev, and then it's a hex number, 8 digits, the 1. And then also have the matching ingress queue, which is how I feed back from the devices, and that's I have obviously also here on this deck. So every device has its own queue out, and then there's a shared ingress queue where we're collecting into, at least right now, this node, and this is an ingress queue on a per node basis, that we can go and collect the responses that the devices are sending us. The advantage of having this device queue is, first of all, as I said, the separation of the API layer and the protocol head layer. So between the cloud side and the device side. If the device were to lose its connection because it sits on radio, it will go and reconnect. It will go and reestablish a connection. If the protocol heads now sit behind the load balancer and you have, let's say, 8 nodes and that are managing connections, it will go and land on one of those nodes. That means that the load balancer is in control and you have a hard time kind of pinning the device to a particular front end. Now, if you have a queue now you have a stable place that all the commands to the device land from the front. And what happens is, as the device connects in, it will simply go to that queue that sits in the infrastructure, and it doesn't matter which of these front-end nodes, which of these protocol head nodes a device lands on. So you have this intermediation of the protocol side, of the device side, and of the API side, where if connections break on either side or load balancing happens, the matchmaking always happens magically because you have the queue in the middle, because you have a stable name for that device. Also, as devices get disconnected, specifically if they're on radio, any kind of radio technology, may that be Wi-Fi, may that be GSM, may that be analog TV white space, whatever the radio technology is, there will be gaps in connectivity, especially if the devices are in motion. The nice thing about having that device queue is that you always have a place to go to, irrespective of that device is still online. And you can define by urgency of the commands, the urgency of the commands by using the TTL that you use for that queue. So if you have a command that needs to be executed right now, like you want to open up a car, well, you stand right next to the car, you walk towards that car, you probably want to have that command happen in 5 seconds or never, because you certainly don't want to have that car open randomly in 2 days. But other commands may have a tolerance of, let's say, an hour or 2 hours to be executed if whenever the device shows up, hand over that command, and having a queue in the middle and the queue be available and have that command ready for whenever the device gets into coverage is something that is enormously useful. And then you can use the dead letter queue, another facility that hangs on the HQ, to go and pick up the result, pick up whenever a device cannot pick up its messages. So you can pick up whether a device cannot pick up its messages because they expired. If the TTL expires, then you can know which commands were delivered or which were not. So you get a temporal decoupling, and also you get a serialization of commands. You might have concurrent clients that are trying to talk to the device all at the same time through the API front, and what the queue does is it now puts them all nicely in sequence by order of arrival for the protocol head side that talks to the device to go and pick up. On the other side, the Ingress queue has the same functionality. If you issue a command, that command takes a little bit longer on the device, maybe because you're actuating something in the physical world, you're initiating a reading of some physical state that takes a long time because the world doesn't work necessarily on microseconds, then it might take you a little bit longer. And sometimes your API node may go down because it gets upgraded. So something on the server side may happen, or something on the client side may happen. The client may crash, or the network connection gets lost. So any kind of failure conditions can happen there, but you're actuating something, you're doing something in the real world. And so that's not necessarily something that's idempotent that you can do again and again and again. So you may want to have feedback of that, and you want to make that feedback permanent. So even if that client connection collapses, the client state collapses, you have a place that the device can go and drop the response into. You can also share that path for telemetry and then deal with bursts by having a queue. And if you have telemetry, physical readings, lots of numeric values, then a queue, as we have it in Service Bus with a gigabyte or 5 gigabyte of storage, is plenty for telemetry to kind of as buffering if you get into stress situations. And again, here you can also use the dead letter queue to see whether as a result that has been requested by a client, and where the client dies or the server even dies. And so if the response is labeled with a TTL and that TTL expires, then you can go and pick those up from the dead letter queue and then see what you're going to do with these abandoned commands, and then go and either notify the client on the second path, email, SMS, whatever, or you can put them into a database where the client can go and look up the results of the actuation. So you have an immediate feedback path if you want, through the Ingress queue back to the client, but also indirect feedback path for longer running results, which you can also easily realize through the dead letter queue. So what you get is temporal decoupling. You get protection against traffic bursts. You get fair order, and you get a much better way to go and independently scale the API level. That's cloud side, so to speak, and the protocol head that sits device side. So let's take a look at the code, the implementation, and the changes that I made to our program, to the program that I introduced in episode 3. The LED blinker application, the Arduino app, remains effectively the same. I made one change, and that is I made the acknowledgement. That was silly to make it a 0. I made that a 1, and actually labeled that too. And that's the only real change that I made. Otherwise, the program is still as simple as it was. It has its own simplest protocol. The switch controller is still our API side. Now, I made this I added some functionality to it. So first of all, it now takes a messaging factory as input. For that to work, I had to go in the setup. So I'm getting the service bus connection string here from configuration. Let's go and take a look at this here. So I'm configuring the service bus connection string. The service bus connection string I get for this I have to navigate to the list of namespaces. So here I get the connection information. That connection information from my key. Here you see the key. Imagine I will roll it before you get it. So this information that you see on the screen right now is not going to be helping you much. This I copy and then put into my configuration there. That key I put into here. And so that's now being put into, so that's going into this run function. The run function then goes and starts up the server and runs the control endpoint. The control endpoint is our API endpoint. And here I've added an inject, the dependency injection library, and I add a dependency resolver, and there I bind the messaging factory to that constant, to the messaging factory that I created. And with that, it gets injected every time one of those controller gets built. So that's the magic how the controller gets its messaging factory, and the messaging factory is how you get to the queues, the device queue here, and the Ingress queue on the other hand. So I'm doing as I'm calling this. So let's go and do this. The device is now currently on. So let's go and turn that off. So I'm going to make this false. I'm going to call it. You see the device turns off. I'm going to go and turn it on again. There you go. So that works. So as I do this, what I do is I go and create a message sender. I create a queue client, and I'm sending a new brokered message to the device queue with the session ID. That's a new ID that I just made up, and I'm setting the TTL to 5 seconds. So if the device is not connected, this command will disappear in 5 seconds. And I'm going to set a property, which is actually the property that the device protocol head will go and evaluate. And there's the command. And then I'm sending this straight away. I'm closing. So that's how the device gets sent from the APIs from the API set. Now the API is synchronous in the sense that it wants to have a response in HTTP. So we go and accept the message session here. This is the demultiplexing, which means we go and take from that one queue, which is the Ingress queue, we pull out just all the messages that have the session ID set to the session ID that is set in. And then if I get a session, then we're going to go receive the message. That's the reply that I'm expecting. I'm looking at the ACK property. And if the ACK property is 1, then I'm going to return an OK, and that's what we just saw. So it's a request-reply path that we do over a pair of queues. One is a per-device queue, and the other one is a shared queue that's shared across devices. And the way I pull stuff out is by going through this session demultiplexing model right here. So let's take a look at the server per se. So this is the logic that actually runs the device endpoint that's being started up. So here, what I do is I have a loop, effectively non-terminating loop, where I'm accepting a TCP client. So I've done that before. But what happens now is, as I accept a new connection, I'm setting up this context, which all lives in this function. And as you might have noticed, I've done away with all this shared, static, variable, very bad part, and now have basically a context that happens on a per socket basis. And once that socket collapses, all that context goes away. So I have a set of pending sessions. Whenever I get a command, I enqueue the session ID, and the connection path to the device is synchronous, and it only goes and kind of send a command up, that command gets entered, and send the next command up, and that command gets answered. So the pending sessions I'm using the queue for. I'm getting the stream from the connection. Now I'm reading from the device as it connects in, and reading the session ID, the device ID. And based on that, I go and create myself a message receiver on that device queue. So that's how how I get the commands from the API. And also I have a sender on the Ingress queue. So now the API sends messages there. I have a device connection on the socket. And then I go into a loop. It's using the task API. And I have three operations that are kind of four operations actually that are going on at the same time. I receive from a queue. I read from a socket. So I read from the device, or I read from the device queue, coming from both sides. And I also have a notion of a ping, and that ping keeps the connection alive by sending a 0 kind of to the device every 235 seconds. I actually adjusted that one. 4 minutes is the timeout on the Windows Azure Load Balancer, so we are sending just early enough here. And again, one change here, it's not a global ping that I'm doing, as I did that before, global timer, but actually I'm now setting this up on a per device basis because I have this nice per connection context that I'm creating here. And now I can say when any of these things happen, either the queue receive completed, or the socket read completed, or the ping delay completed, or we're told to close, then I will go and unblock here. And now if the socket read completed, I'm going to go and read it off. If it's a ping frame, if it's not a ping frame, then I'm going to send my response, the response I read from the device, the ACK, into the Ingress queue, which now label it with the session ID of the pending session. If I get a message from the queue, I will get the command that I set up in the previous code. If it's an on, I will go and enqueue the pending session. I will write the command up to the device. We'll then complete the message. I've done it. I'm done with that message. If I couldn't do any of those things, if connectivity collapses, I will see that message again, so it's robust. And then I will also cancel the ping timer because I just sent the message to it, so we don't need to go and do that ping. So the ping gets set up again as I go to the top of the loop and waits again for 235 seconds because we've already done that ping now. And with off happens the same thing. And then if it's the ping delay and the ping delay wasn't, if it was canceled, then we're just going to go and set up the cancel thing again. And if the ping wasn't canceled, then we're actually going to go ping it. And that was the entirety of that loop. So what we do is we read from the queue, get the commands and translate them into the native protocol of the device and send them off. We collect data from the device and write that into the queue that goes down. And then we're doing the pinging kind of on the way. And that gives you that kind of installation. You can go and shut this down. You can go and bring this up again, and we can go and now start taking that controller and that server and rip them apart and put them into separate processes. One sits in a web host, the other one sits in a worker host, and that's also something that we're going to do down the road as we're expanding this into a more scalable architecture. So much for this episode. What we're going to do in the next ones is we're going to do some theory. So I'm going to do some whiteboarding to talk about things like scaling this out, and also go through protocol options, and also talk about security concerns, because we have still not, even though we have now service-assisted connectivity, which means we're now enabling the device, we're helping the device to defend itself. We still don't have any security, true security in the sense of protection against eavesdropping or modification of the traffic. So we'll have to go and talk about those options also specifically in the context of small devices. Thank you for listening to this episode. The code is on GitHub. The address is here and also obviously in the blog. See you in the next episode.